Our final section on exponential and log functions involves applying them to models of real-world events. And we'll look at models that involve the sciences from biology and engineering and physics to banking and population growth. Let's look at a few different types of exponential models. The first type is population growth models, and these involve exponential functions whenever the population grows at a constant rate relative to the current population. For example, if I tell you the population grows at 5% per year, I'm saying that each year we take the current population and add 5%. And so the next year we add 5% to the already increased population from the year before, and so on, and that behavior leads to exponentially increasing populations. And so this is an important application in biology to bacterial cultures and also to modeling of human and animal populations under some circumstances and for limited periods of time. Another example is to radioactive decay of radioactive elements. And the way we speak about radioactive decay is usually in terms of the half-life of the element. And the half-life of the element is the time it takes for half of the element to have decayed away. And so it's very similar to the population growth where we talk about a certain percent being added each year. In this case, we're talking about over a certain amount of time, 50% of the element has gone. And so this is a decay, an exponential decrease, that models the amount of an element over time. And so this is an exponential that decreases towards zero. Given enough time, the element would decay away completely. So these two have something very important in common, and that's the idea that the amount of the material, the amount of people in the next time interval is proportional to how many were there previously. For radioactive decay, that's a decrease. For population growth, that's an increase, usually. But they share that common feature, and whenever you see that feature, that the rate of change is proportional to how much you have currently, you can expect to see exponential growth. And it's that feature that makes exponential growth so common. Another similar example is continuously compounding interest. If your bank pays you interest once a month, then each month it's compounding the interest, it's adding the interest to the amount you already have, and then the next month calculates the interest on that new amount and so forth, and keeps adding the interest in, and you earn interest on the principal and that interest. In this case, we're going to start with an initial investment, what's called the principal, and we're going to invest that over time, and that principal is going to increase exponentially. And so this is a plot of money against time instead of population against time or a radioactive element against time, but the idea is very similar. As a final example, we can think about Newton's law of cooling, which states that if you have an object of a certain temperature and it's in a room with a given ambient temperature, so basically the room temperature, there's our ambient temperature, yellow is the temperature of the room, over time it's fixed. And if I put, say, a hot object like a cup of coffee in that room, over time that cup of coffee decreases in temperature from an initial temperature, let's call it T0, and Newton's law of cooling states that that decrease is exponential. So the temperature of the coffee cup decreases exponentially towards the temperature of the room. Asymptotically, the coffee and the room are at the same temperature. So that gives you an idea of the kind of ways you can use exponentials in real-world models. Let's look at a few examples. For our first example, we're going to look at radioactive decay, which is a process under which heavy elements undergo decay and the amount of that element will be reduced over time. We assume that this decay happens in an exponential manner, and so just like the population growth, we've got a very similar equation for the amount of the substance, usually the mass of a substance, with time. We need to know the initial amount, which we'll call A sub 0. It's the amount at time t equals 0. And we need to know the rate of decay. This k in this case is called a decay constant, but because it's decay, this value will be negative. So let's look at an example. We're going to look at the radioactive element thorium-234. The important thing here is that thorium has a half-life of 578 hours. Half-life is the amount of time it takes for the substance to decay by half. In other words, to halve the initial value. So if our initial value is A sub 0, then after one half-life, we'll be left with half of that amount. So if we call capital T the half-life, then we know after that amount of time, there will be half of the initial value left. So after a time capital T passes, we'll be left with half of A sub 0 as the initial amount, and plugging that time into our formula, we'll have A sub 0 e to the k capital T, where capital T is our 578 hours. We can cancel here this initial amount we have 1/2 is equal to e to the kt, and so taking the natural log of both sides, we end up with kt is log of 1/2. So k is 1 over t times the natural log of 1/2. And using 578 hours, we can calculate k, and we find it's negative. It should be negative. If it's not negative, we're in trouble. 0.00119922, and there's more detail. I'll use the exact value when I do calculations, but that gives us an idea. So now we know the decay constant. That's our first job every time. If we're given a half-life, we can find the decay constant. Once we have the decay constant, we can write down the equation which governs the decay. And that equation, we still don't know an initial starting value, but we know this decay constant, and so just plugging it in. And so in the part A of the problem, it tells us what the initial mass is. The initial sample mass was 50 milligrams. So just plugging in that initial mass, that gives us the mass of thorium as a function of time. It's 50 times this. So let's look at the next part. So what we found in part A was this formula for the amount of substance at a given time, and the constant up here was given by log of 1/2 over 578, and that has units of per hour because 578 was in hours. So if we want to calculate the mass after 100 hours, that's a simple process of plugging 100 into the formula. This is 50 times e to the kt, and that turns out to be about 44.35, and this is, we started in milligrams, so this is in milligrams as well. So we started with 50 milligrams. After 100 hours, that gives us about 44.35 milligrams. We should always ask if that makes sense. And seeing as we started with 50 milligrams, and we know that the half-life is 578 hours, in other words, after 578 hours, we expect there to be 25 milligrams left, then it doesn't seem unreasonable that after 100 hours, we've still got 44 milligrams left. So this is reasonable. If it was less than 25 milligrams, we'd be in trouble because that's the half of the starting amount, and it should take 578 hours for that amount of decay to occur. So part C asks us when there's 10 milligrams remaining. So again, in this case, we're looking for the time when A of t is equal to 10. And we started with 50, and we've got e to the kt, where the k is the same k from above, so I'm just going to write k. So I could write this as 10 over 50 is equal to e to the kt, and 10 over 50 is 1/5. And now taking the natural log, this is the natural log of 1/5. And on the other side, we get the natural log of the exponential of kt, and so that's just going to be kt. And so we find that kt is equal to the natural log of 1/5, and so the time in this case, given precisely, is the natural log of 1/5 over k, where k is that value up there. And if we approximate that, we find 1342 hours. Let's see if that makes sense. If you think about the half-life, then initially we had 50 milligrams. And after 578 hours, we should have half of that. So we should have 25 milligrams. And after 2 lots of 578, which is 1156 hours, we should halve that amount again. This is the point with half-life. After that amount of time, the initial amount has decayed by half. So imagine starting again with 25. After another 578 hours, we have half of that, which is 12.5 milligrams. So we were looking for 10 milligrams, and we found that it takes about 1300 hours, which makes sense. So somewhere under 1200 hours, we'll get to 12.5 milligrams. After 1300, so another couple of hundred hours, you will reduce 12.5 down to 10 milligrams. Another example of the use of exponential functions is Newton's law of cooling. Newton's law of cooling, or warming as well, allows us to work out how the temperature of an object changes when it's put in a room with a constant temperature. So we've got an environment at a constant temperature. You can imagine a room with an ambient room temperature that doesn't change. And we're going to call that T sub m. And if you put an object that has a different temperature, let's say it starts with temperature T sub 0, in a room that's got temperature T sub m, our assumption here is that the temperature is going to decay exponentially towards the ambient temperature. So for example, if you had a cup of coffee in a room, then that cup of coffee's temperature will exponentially decrease towards the temperature of the room. And you can see that in this picture. So on this top line here, you can imagine that you've got a cup of coffee and the coffee starts pretty warm, and this is the temperature of the room, the ambient temperature, and the temperature of the coffee is exponentially decreasing towards the temperature of the room. Whereas if you start with something cold, like a can of Coke in the room, its initial temperature, which we're going to call T sub 0, is, and that's the temperature at time 0. As time passes, here's the time axis, as time passes, the Coke is going to warm up, and it's going to warm towards the ambient temperature. So exponentially, the temperature of the object placed in the room is going to tend towards the temperature of the room. And that's what this formula embodies, and K here is the sort of constant, and it has to be less than 0 because this term decays away and eventually you're left with the ambient temperature. So let's look at an example. Let's suppose we've just taken a turkey from the oven and the turkey is uniformly 170 degrees, so the entire turkey is 170 degrees, and the room that we placed the turkey in is 70 degrees Fahrenheit. So after 5 minutes, the turkey is cooled a bit to 160 degrees. That information lets us find the constant. We know that the room is 70 degrees, that's our ambient temperature, the T sub m. We know that the turkey itself is 170 degrees initially, and that gives us some constants to plug into our formula. Our job is to find that K. So recalling this formula, we can just plug in the information we have, and we see that we can simplify this down to 70 plus 100 e to the kt. The only value we don't know, apart from the variable t, is this K. So that's our job, find the value of K. Now we know that after 5 minutes, the temperature of the turkey was 160 degrees. So that gives us information that we can use to find K. And that's what you should always look for in these problems, that we're given information that will let us find that growth constant. So rearranging this equation, so dividing the 100 over, cancelling the extra zeros, we've got e to the 5k, just this term here, is equal to 9/10, and that tells us what 5k is, because if e to the 5k is 9/10, then 5k is the natural log of 9/10. And that we can then calculate and find that k is 1/5 of that value, 1/5 of the natural log of 9/10, which works out to be about negative 0.0211. Now, this is less than 0. If we had got a k that wasn't less than 0, we know we've made a mistake. So now we can go back to our initial thing and we could plug in that value, and that gives us a function that lets us work out the temperature at future times. For example, we want to know the temperature of the turkey after another 15 minutes have passed. So that's another 15 minutes, so what we're asking for here is t of 20 minutes. The only time we've used in here has been 5 minutes, and so the units we're dealing with are minutes. So we're just going to plug 20 minutes in here. And that all comes out to be about 135.61 degrees Fahrenheit. So I hope these last few examples have given you an idea how the exponential and log functions and our skills with manipulating them can be used to look at problems that involve real-world applications. So it's time to have a go at some problems. Thanks for tuning in.